So, we've all been promised this incredible future, right? A future of seamless, self driving cars, just gliding from one high tech charging pad to the next, while we kick back in the back seat, read a book, or just catch up on emails. Welcome to This Explainer. Today, we're actually looking right past that Silicon Valley hype. We're going to dive into the hard data, the actual physics, and the literal concrete infrastructure realities that are keeping that beautiful sci fi future just out of reach right now. There's a massive tension building between this rapid software scaling and our messy physical world, and we're going to break down exactly what is bottlenecking the whole revolution. Okay, here's our roadmap for today. We're starting with scaling the EV network, then moving right into automating the robo-taxi charge. After that, we'll look at Tesla's aggressive expansion plans, and finally, we'll unpack the autonomous safety bottleneck. All right, Section 1, scaling the EV network, focusing on the public charging bottleneck. Because, to understand the future of transportation, we really have to look at the massive physical footprint required to power the whole thing. To combat those grid constraints and those long queue times we all dread, charging networks are heavily pivoting to a bigger is absolutely better strategy. A great example is Electrify America's Cycle 4 strategy. They're building these massive gas station-style hubs. Take a look at their new San Francisco flagship location. It's got 20 hyper-fast, next-generation chargers that can deliver up to 350 kilowatts. To put that into perspective for you, a 350 kilowatt charger can theoretically add 100 miles of driving range in literally just a few minutes. They're building these massive, high-output locations for one simple reason. Everyday commuter demand means they just have to. And the raw data shows exactly why these mega hubs are so critical. Just look at this. Between 2024 and 2025, California saw a massive 24% year-over-year increase in gigawatt hours dispensed across the network. But notice, that's compared to a much smaller 14% jump in actual charging sessions. That discrepancy is absolutely crucial. It means it's not just that more cars are showing up to charge, it's that those individual cars are demanding way more power per session. The sheer volume of energy moving through these cables right now is staggering, and it's putting an unprecedented amount of pressure on our existing infrastructure. So to handle all this extreme throughput, networks are getting creative. They're deploying some really clever operational hacks. For example, Electrify America recently instituted a strict 85% state of charge cap across over 90 of their busiest California stations. It's kind of like packing a suitcase for a long trip, right? Throwing in the first few layers of clothes is fast and super easy, but squeezing in that final 15%, that takes the most time and effort. By just cutting the charging session short at 85%, the network dramatically slashes wait times for everyone else in line. It keeps the physical line of cars moving and massively boosts the station's overall daily efficiency. But managing impatient drivers is really only half the battle here. The other half, managing the actual electrical grid. Imagine the localized strain if a dozen massive batteries all plug in at exactly 5 p.m. To keep local neighborhoods from facing brownouts, networks are pairing these megastations with battery energy storage systems. There are actually over 120 of these deployed in California alone, and together they operate as a massive virtual power plant. Basically, they draw power really slowly at night during off-peak hours when electricity's cheap, and then they discharge that stored power directly into your car during the peak afternoon rushes. It's a total game changer, mostly because it completely avoids the need for utility companies to build costly new power plants just to handle the EV surge. Moving on to Section 2, automating the robo-taxi charge and the fleet bottleneck. Because while public networks are figuring out everyday drivers, massive autonomous fleets face a totally different logistical nightmare back at the depot. It's a surprisingly simple question, isn't it? If vehicles drive themselves, who plugs them in? Picture thousands of self-driving cars returning to a dark, sprawling depot at 2 a.m. You simply cannot run a fully automated, scalable ride-hailing service if it relies on a small army of human workers running around in the rain, manually dragging heavy, high-voltage cables all night. The labor costs and the operational inefficiency of that one manual step instantly becomes a severe barrier to scaling any fleet. So we are currently witnessing a massive operational shift to solve this exact depot bottleneck. Look at the current reality. Market leaders like Waymo still rely on human workers to manually plug in their 3,000 vehicles scattered across 10 major U.S. cities. But the future of fleet operations, it looks a lot more like Roxy's new M1 overhead robotic system. Instead of human hands, you have an AI-powered robotic arm that autonomously detects the car pulling up, opens the charge port, and seamlessly plugs it right in. And get this, it hits an incredible 99.9% success rate in live environments, literally with zero human intervention. But here's where the math gets really fun. The true genius is their multi-bay approach. Because a single robot can glide along an overhead rail and service 10 different parking bays, a 50-day depot doesn't actually need 50 expensive robots. This setup lets fleet operators squeeze out 75% higher operational efficiency from the exact same real estate. And when you look at the unit economics of a robotaxi business, saving up to $1.7 million annually isn't just a nice perk. Solving this bottleneck is an absolute make-or-break requirement for the business model to ever reach profitability. All right, Section 3, Tesla's aggressive expansion plans. Let's look at the timeline promises. How does all this automated infrastructure actually build toward the grand promise of fully autonomous fleets? Well, let's take a look at Tesla's current ride-hailing rollout. During their Q1 2026 earnings call, Tesla laid out a wildly ambitious roadmap. They promised to drop their robotaxi service into 7 major new cities by the first half of the year. And we're talking complex, sprawling metros here: Dallas, Houston, Miami. Plus, their stated target is to reach a dozen or so states by the end of 2026. Now, scaling a heavily regulated autonomous ride-hailing service to a dozen states in a single year, that is a blisteringly fast operational pace, no matter how you look at it. But there's always a but, right? Impartial investigative reporting by Reuters shows a pretty stark contrast to those grand promises when you look at the passenger reality on the ground today. Reporters documented agonizing 36-minute waits with no rides available messaging in major hubs like Dallas. And when the cars do finally arrive, their programming often entirely avoids complex highways. So your standard 20-minute highway drive turns into a 35-minute crawl down local surface streets. Imagine ordering a premium robotaxi only to be trapped inside a tiny operational geofence, or worse, getting dropped off at a boundary line that forces you to walk 15 minutes to your actual destination. The ground reality is definitely struggling to match the hype of the earnings call. Which brings us to Section 4, the autonomous safety bottleneck and the data behind the delays. You see, those weird routing choices, the tiny geofences, and the long wait times, they aren't actually just convenience bugs. As we dig deeper, we find they are strict safety parameters hiding a much bigger constraint. Let's look objectively at the raw, unredacted NHTSA data from their operations in Austin. The math really tells the story here. Tesla's robotaxis are currently logging a crash rate of roughly 1 per 57,000 miles. Compare that to your average human driver, who crashes roughly once per 229,000 miles. So right now, the autonomous system is crashing roughly 4 times more often than a human. This mathematical reality is exactly why these fleets are intentionally kept so small and why they restrict their routing to slower, highly predictable surface streets rather than fast-paced, unpredictable highways. Now, we all know autonomy is notoriously difficult, but it gets crazier. Newly unredacted reports show that even the remote control backups are struggling. Yet records show that even when remote human teleoperators completely take over to just inch the vehicles along at speeds under 10 miles per hour, low-speed collisions are still happening. We are talking about highly advanced, multi-million-dollar vehicle platforms slowly mounting curbs to hit metal fences or just gently bumping into temporary construction barricades, all while a human is actively monitoring and steering them remotely. Which actually brings us to this powerful quote directly from Elon Musk during that exact same earnings call. He openly stated, "Rigorous validation, making sure things are completely safe. We don't want a single accidental injury." It's a huge acknowledgement. What's holding back the future isn't a missing line of code or a manufacturing delay. It's the incredibly messy, heavily regulated business of physical safety validation. Proving that a 2-ton machine won't make a single critical error is the absolute bottleneck preventing immediate, massive scale. So here's where we stand. We are successfully building the high-voltage grids. We're building the automated robotic depots of tomorrow. The physical world is rapidly getting ready. But I want to leave you with this final question. As we build out all this infrastructure, can the artificial intelligence behind the wheel actually scale safely enough and quickly enough to even use those multi-million-dollar depots we're building today? Thank you so much for joining me on this explainer. Keep questioning the data, and we'll catch you next time.